Can everyone see that okay? Yeah, okay, I'm gonna share use. Okay, let's see. Okay, hello, how are we doing? Good, okay, how do we feel after last week? Yeah, good, great, okay. Makeup exams I have in my possession, so if you have extra time. So I am scanning those tomorrow morning, and grades should be out shortly. And then y'all can yell at Dr. Liddell. Any questions about the exam? Any questions about how that's going to work in the future? Okay. Okay. I think that's all I have to say about that right now. What would we like to see today? I think we covered like rate laws and rate of reaction in class today. Is that just something we want to go over? Is there something from the past exam we want to see? Go ahead. Can you do like equations that you could ask about the rate? Yeah, absolutely. Okay, so one thing to note about rate laws in general is that they right, he goes through a lot of stuff where he's like, this isn't actually the rate of the equation, or this is the rate of the reaction, and this is how you define it. And there's a lot of integrated math and taking derivatives and stuff. You don't need to worry about that. As long as you know the equations that we're going to go over, you should be okay to answer the questions that he throws at you. Based off of his previous exam, right, he might ask you like, how would you, what is that thing that you're taking, right, the tangent line to the rate of the rate, or to that graph. That's something you might need to know, and that might be like a true false type of question. But actually like deriving those equations is not something that you need to know. So I guess the most simplest thing that we can talk about first is just regular chemical reaction. So we can have A plus 2B goes to C. And we can all see that up there. That's okay for everyone? Yes, okay. Okay, so the big thing between a rate of a reaction is just how quickly our reactants are turning into products, right? So over time, A and 2B are going to come together to form C, right? So that might be something like water, or right, your hydrogen and oxygen are coming together to form water, something like that. Okay. So what the chemical equation is telling you is that for every 1 mole of A, or for every 1 of A, we can call it, right, we need 2 moles of B, right? That's just what our coefficients are telling us. 2 times the amount of B is required for A to form C, right? We have a 1-to-1 ratio between A and C are 1-to-1, but then B to C is 2-to-1. Okay. And that's important for all of our rates, because what one's going to be used up faster? If we have equal amounts of A and B, which one will be used faster? B is going to be used faster, right? If we're trying to make a sandwich, we have 1 slice of bread, or sorry, we have 1 slice of ham and 2 slices of bread. So if we only have 10 of each, we're only going to be able to make 5 sandwiches, because we have 2 slices of bread that's required for every sandwich we make. Okay, so this is just telling us that this is going to require 1 mole as well. So this used up faster if you start with equal amounts. Okay, so if we were to give you a graph, and we were to say, this is our concentration. Sorry, this is our concentration. Okay, time is going to be on your x-axis, concentration is going to be on your y-axis. Where would your reactants start? Would they start at 0, or would they start higher up on the graph? Higher up, right? You're starting off with reactants. And are they going to decrease or increase over time? Decrease, right? So 1 might start here and go like this. then one might start here and go like this. Out of A and B above, which one was the red line be A or the blue line be B? Or would the red line be A or the blue line be A? Why do we say red? Right, it has less of a steep slope. It's going to be used up slower than your blue line or your B would be. So this is going to be A. This is going to be B. What would your C or your products look like? They would start at 0, and then it doesn't really matter. Doesn't really matter where that line ends up. It might be below A, it might be below B even. But this would be your C, right? That would be your products. You're going to start with 0 products, and as the reaction happens, it'll form them. Does anyone know what like this region is called? You know what we've reached when we plateau? Something we fully talked about yet, so great job. Okay, any questions? So just like a graph of what reactants being used and products being produced. Show and how to tell which is which. Good? Okay. So now we're looking at equations and stuff that we can do with that. Again, looking at our A plus 2B goes to C. We go through this whole thing of deriving what the rate of the reaction is and what it boils down to. But essentially, we can break it down where that your change in concentration of A over your change in time is equal to the change in the concentration of B over the change in time, which is equal to the change in the concentration of C over the change in time. But there's a couple things that we have to add to this ratio in order to make it correct. Yep, negatives for A and B. I guess I'll put those in red. Perfect. Yep, and we need a 2 here.
Why is the 2 attached to the change of time?
It's the whole thing. It would just be like a 1/2 times this, but in terms of fraction math, 1/2 times a fraction would just be 2 times that. So it's really 2 times this whole thing here. Okay, questions so far? Your reactants are going to get the negative portion of that rate because your change in concentration is always going to be T final minus T initial. And what we saw from our graph, right, T final might be this point here. And this is T initial. Concentration final, concentration initial are also at those same points. So that lower concentration is going to be a lower minus a higher number, which would always create a negative. Okay, so that negative in front would eventually make your answer a positive for the rate, because you will always have a positive rate of reaction. Okay, but you should know that all of your reactants will always have a negative in front of this in this equation here. Questions on the negative? Okay, questions on the 1/2? The 1/2 is going to be the same for all of your reactants, where it's just the reciprocal or the inverse of that coefficient that it's flowing. Okay, so if we have something where it's 3A plus 6B goes to 7E, because I started writing a line, right? Those would all be, it would be 1/3 times delta A over delta T, which is equal to negative 1/6 concentration of B over time, which is equal to 1/7 change in concentration of E over change in time. Okay, so it's always going to be that inverse. If it was even 1/2 A, goes to B. This is now 2 times negative concentration of A over delta T, right? We're just taking that inverse. We're flipping whatever that is in front to the opposite. Any questions there? Right, you can prove this to yourself mathematically. We said that B is going to be used up twice as fast. So if A has a rate, right, of, let's just say 5, right? A has a concentration or a rate of 5. In order to find B, we would know that it would be twice as fast. So B would be 10. So in order to make those equal, we have to divide the 10 by 1/2. Okay. And that's always something that you can do with these. You can always prove to yourself that the reactant that's being used faster needs to be divided by something in order to make it smaller. Any questions? I think that's really all that you need to know for that. You could find also the main point behind this too is that whatever this negative or this concentration of something, it's this portion here. When it becomes dx over dt, this is the rate of reaction. Right, we can approximate it and we can do some fuzzy math in order to say that, right, concentration over time is going to give us the rate of the reaction. But when it becomes that dx over dt, that's when it is the actual rate of reaction. If you use the rate of reaction if you're given a rate of reaction for A, you can use this above equation here, this one, in order to just plug that in, right? You can plug in that rate of reaction to find the rate of reaction for B or the rate of reaction for C. That way, that whole portion just becomes like an X, and you can solve it for it that way. Yes. Yes, we'll finish up all the rate stuff and we can do that. Yep. Any other questions so far? Okay. And then the next thing for rates is just your rate laws. Or your rate, these are actual like rate equations. Okay, so your rate laws, does anyone know what can go into a rate law or what is included in a rate law? Yes, yep, so what's included? We have our rate constant, and that's little k. What else is included? Does a product go in a rate law? A reactant's going to go in a rate law? And what's the power included? What is that called? Yep, and then we have the order of the reactant. So what that boils down to is that it is the rate of something is equal to little k times A, we call this M, times B, we call this N. Okay, so this is rate constant. These are your reactants. And these are your orders of reactants. How do we find the overall rate order? For the overall reaction, we don't need to slope of the line. Yep, perfect. So your overall rate order is the sum of reactant. So here, this would be M plus N.
For the reaction in class, we had them, I think, below, like, the brackets, we have matters below.
No. It's just saying that it's like your concentration of A, so it just depends on the concentration and stuff, yep. Any other questions? Yes.
I know the textbook you did specification, sometimes we have ABC.
Mhm.
Does that find it as the only few reactants, not saying C as a product?
Yes, it's only saying reactants. In that case, you just have 3 reactants that you're looking at. Yep. Anything else? Yep.
So how, on the there value?
Yep, so I believe you'll talk about that more on Friday about how to experimentally find them. But basically you just have to do some math. You'll be given a chart and you might remember this from high school if you took it. But you're given like 3 trials and then your concentrations are changing in 2 of them. And then being held constant in 2 of them. And so you just have to, you write 2 rate laws and then do some math. We can go over that after you've learned it. It's kind of fun. You're just kind of making a puzzle. And those are pretty straightforward once you get the hang of how to do them. Okay. Let's see, what else? Does anyone know the units of little k, the rate constant? So it's kind of a trick question. So k units are constantly changing. Depending on the overall rate order. Okay. K will always have the generic unit of concentration over a time unit, right? Rate units are molarity over second sometimes, right? Maybe it's molarity over minute, molarity over hour, it might be, but it's some sort of time component on the bottom and concentration on the top, okay? So in order to get to the units of K, you need to look at how many concentration units you're multiplying on the right-hand side. So if we have a rate where K is A and then B squared, what is our overall rate order for this equation? It'd be 3, right? What's the rate order of A? A is 1. What's B? 2. So overall, we have 3. Questions on how we found that? Okay, so how many times are we multiplying concentration together? How many times? Yep, how many times are we multiplying concentration together? 3 times, right? If we were to break up this here, this becomes A times B times B, right? If we were just to plug in the units for what concentration would be, it would be molarity times molarity times molarity, which is molarity cubed. Questions there? Okay. if our rate is given to us in molarity over seconds, right, we can now say that molarity over seconds is equal to K times molarity cubed. How do we solve for X or K here? You don't have to do that. Because cube rooting it would still keep K with N. Yeah, you can just divide by molarity cubed. Divide by molarity cubed, right? You have a fraction over a fraction, so it ends up that molarity over seconds. Molarity over seconds times molarity cubed. And so we get 1 over seconds times molarity to squared. Okay, so your units for K are always your time unit, whatever that may be. Seconds, hours, minutes, milliseconds, doesn't matter. Your time unit to the -1. Right, -1 will then put it on the bottom, so it ends up in the bottom of your fraction. Times concentration, molarity, to the negative overall rate order. Minus 1. Right, if we look at our overall rate order, we said it was 3. Just to prove it. We said our overall rate order was 3 minus 1. We get m to the -2, which then means that we have 1 over n squared. Right, and that matches what we have in black that we just solved for. Was always 1 less than your overall rate order. So if your rate order was 6, then the exponent on molarity would be 5. Right, if your rate order was 0, that would be 0 minus 1, which means you have molarity to the -1, which makes it molarity to the 1. We push it on top. Okay, so then you still get molarity over seconds. You can practice it and prove it to yourself, but this is always a good trick that I know if they're looking for units of K. Questions there? So I think so far in lecture, that's kind of where you end for rates and equations that you talked about. Does that help? I forgot who asked. Was that you? Does that help cover what we kind of did in class today? Yes. Are there any more questions on rates, rate laws, anything like that? Feel better? Okay, so then we talked about, or we wanted to talk about osmotic pressure. Let me actually find that. Let's check. Those slides. Equation. You don't work a lot with osmotic pressure besides Gen Chem. So if it's very confusing, you don't get it, that's okay. It'll probably only be like 1 question, if that. How do we feel about Le Chatelier's principle too? I just go by it. We feel good with that one? Okay, I like that one. I think this is like the end of module 1. So essentially what's happening with osmotic pressure is just something that is looking at solute dissolved in a solvent. So we have a beaker of water, right? And this is just pure water. Right, if you think of this as a pot on a stove, right, you're boiling some pasta, but you didn't salt your water. So you just have pure water here, okay? That's gonna boil faster than if you had little salt particles in your water, right? This is because, right, we talked about vapor pressure and that fun stuff there. This is just because, right, it's going to boil faster. There's more stuff in your solution. It cannot heat up as fast. It has to work around those now salt molecules that are in your solution. Anytime you add anything to pure water or any other pure substance, it will always have a lower vapor pressure and then also, therefore, osmotic pressure as well. Okay, but it's just telling you that, right, this is going to affect the kinetic energy of your system. Let me just read these again. Okay, so if we were to put this in one beaker, okay, and we had a little divider between them. This side is pure water. This side has your little salt particles. At some point, right, these molecules are going to start dissolving into the other side, right? They're going to start moving to the other side. Eventually, we will come out to a solution that looks like this guy. Right? Over time, it's going to spread out altogether. Okay? The point of osmotic pressure is that it's not the particles moving towards the pure water. It's that the pure water is moving towards those particles. Does that make sense? Okay. It's not these guys moving this way. It's the pure water trying to make the concentrations the same, right? This is at 0. This is at 10. The water is going to slowly move to this side in order to decrease that concentration so that it matches what's on the left. Does that make sense? Yes, no. It's very weird. It mostly has to do with like your red blood cells. And then I feel like there's one other example that I can't think of at the moment. You don't use it a lot unless you want to be someone that works with blood all the time. Probably not super important. But that's essentially what osmotic pressure is. I think that's all I have to say on it. Are there any other questions with it? Do you remember what the formula is?
Pressure,
Mhm.
pressure,
Pi times volume is equal to nRT. Yes. So it's very similar to what other equation that we know?
gas mass.
Yeah, our gas law or our Pivnert kind of thing. This pi is telling you that it's osmotic pressure and not your normal P pressure. Okay, it's that difference in pressure that we're talking about, that lower vapor pressure it might be, in order for that to be the osmotic pressure. I don't think there's anything, any like indicator of like you know it's osmotic pressure unless he tells you that it's osmotic pressure, or that you know that it is something being dissolved in solution. I know that there was like, I think one homework question or one practice test question about osmotic pressure. But that had to do with your red blood cells. And so you basically just had to do this equation here in order to solve for that one. I don't know. I don't think I solved that because I knew y'all skipped it. Look at that. I don't remember if it was in the homework. Yeah, okay. So question was, alrighty, so we have the average osmotic pressure of blood is 7.7 atm at 25 degrees Celsius. What concentration of glucose, not ionized, would be isotonic with blood? Okay, so what do we think? How would we solve this? What do we know and what do we not know? What is pi here? This is your pi. And we know our temperature here is 25 degrees Celsius. Yes, we could do that. We need yeah, we don't have a volume. So we don't have a volume, we don't have n. How do we get that from pi v times nRT? Yes, but what else do we need to solve for? Is there a way that we can rearrange the equation so that it ends up as moles per liter? Who said yes? How do you do it? Right, we're going to divide by RT, so we end up with pi v over RT is equal to n. And then also divide by v. So we get pi RT times n over v. Oops, not times, excuse me. Equals n over v, right? So we're solving for n, but we're also solving for v at the same time. Does that make sense how we're going to do this? What R are we using? Yep, we're going to use 0.08206 because this is in liters times ATM over mole times Kelvin. And so our ATM from our pi will match the ATM in the gas constant. What else do we need to do before we can plug everything into our equation? Yep, we need to change our temperature of 25 degrees Celsius to Kelvin. What is that going to be? Awesome. So we have our 298 Kelvin is equal to T. Okay. So we said that we have pi RT equals N over V. So this looks like 7.7 ATM over 0.08206 times 298. And I got 0.3149. How many sig figs would we round to? We're going to round to 2 sig figs. So this would be 0.31 moles over liters. Does that make sense how we would do that pressure, osmotic pressure, and how we would do that question from the homework now? Yes. Yep. So, right, our initial equation was NV equals nRT. Oh, I'm sorry, I made a mistake. This is. Okay, our initial was pi T over nRT. We're looking for something that's moles over liters. So N is going to be in moles for units and liters is going to be the volume for units. So we're trying to rearrange our equation so that it ends up as NV is equal to something else, right? So I could have divided by V first to get pi is equal to nRT over V. And then I could have divided by RT here. Okay, and then that would have canceled out. So then we still end up with pi RT is equal to N over V. Does that make sense? Okay. Yep. Yes, you could have also done that. So if you done that, you could have said that liters is equal to, or not liters. Your volume is equal to 1 liter. And then you could have done pi V is equal to nRT. And then you could have said 7.7 times 1 is equal to N times 0.08206 times 298. And that would have ended up with the same thing. It's just if you're trying, right, you don't know a volume and you don't know a mole, so you could have just solved for it in all in one, or you could have assumed 1 liter, and that would have been fine too. Unless it's what you're trying to solve for, yes. Most of the time, if you just have like 1 liter or something else, you can assume most of the time, or if you have like 100 grams of something, then that's usually okay. Like if you have 100%, then you can assume you have 100 grams of something. Like that assumption is always fine. Yep. Anything else? Yep.
I was just asking, all right, what concentration wants us to like relate how many grams of glucose to the volume of the body?
It's trying to relate molarity because he tells you here, he tells you you want it in M, which is in molarity. And so he wants you, what he was testing you there is, do you know that molarity means moles over liters? Okay, so you just need to know your different concentration units in order to figure out what you need to solve for. Yep. Does that help your osmotic pressure question? Okay. What other questions do we have? In N, yes, yep. It's much more clear typed out. How are we feeling? Yes? Anything else you want to see right now? Want me to just kind of give you a couple questions? Practice? Does that sound, yeah,
Do it a practice.
absolutely, yep. What I could give you is one more thing about rate laws. Your half-life is the time it takes for 1/2 of the reaction of the initial reaction concentration to exist. I believe this is part of these notes. Did you talk about half-life today? Or am I talking? Okay. So that's just one thing that you talk about on Friday. But does anyone know where we hear half-life stuff? Yep, radioactive decay. And you'll talk about that more on Friday. But I just want to make sure I talk about that now because that'll probably be a part of your homework. And all that fun stuff there. Okay. Did you talk about straight line curves today too? Or is that you stopped at rate is equal to K units, right? Okay. I read a little bit of ahead, so I wasn't exactly sure where y'all stopped. Okay, so let's see. All right. So we have 4 questions that we can answer. We have a reaction A plus B goes to C is first order for reactant A and B. All right, so A is first order, B is first order. So I want to know what is the rate law equation. So that's like the rate equals 1. I want to know what is the overall, sorry, not rate law. What's the overall rate? Order, sorry. And then I say that if the rate is 0.5 molarities per second and the concentration of A is 0.05 and B is 0.1, what is the value for K? And then given that K you just solved for, we're changing the concentrations of A and B, and I want you to find the rate of the equation. Okay, do you want to do that together? Or do you want to have a couple minutes work in a row? Do it with me. Alrighty, so initially, what is the rate law equation? What is that going to start off with? Yep. Right, so we'll have rate is equal to K times the concentration of A. Do we know what the exponent is? It's going to be 1, right? N is equal to 1 because we know that it is first order from the question. So we can just leave it as A. And then what's it going to be multiplied by? B. Does that get an exponent? Nope, we're all good to go. And so that would be it, right? We don't know what K is. We don't need to fill in K. And so we can just leave it as K times A times B. Questions there? Okay, I just want to point out that even though that there's a coefficient of 1 in front of A and B in this top portion here, right? That does not mean that it is first order. This still could have been a 2 here, and this could have been a 3, and they still could have been first order. The coefficient does not matter or relate to the order of the reactant unless they're in a specific condition that we haven't talked about yet, okay? So for right now, the coefficients do not relate to your rate law. You have to either find it empirically or be told it. Yes. Yep. So anytime anytime moving forward, we're gonna stick with that rate is equal to K times A times B. Okay. Any questions on 1? Okay. What is the overall order for this reaction? 2, and how do we do that? Yep, we just did 1 plus 1. Right, we said it's first order for A, first order for B, 1 plus 1 is 2. Questions there? Okay. Okay, so next we have if the rate is 0.5 molarity per second, and the concentration of A is 0.05 and B is 0.1, what is the value for K? How are we going to solve this one? Yeah, awesome, right? So we start off with rate is equal to K times A times B, right? Those brackets mean concentrations. We can plug in a concentration for those A and B values. We're given the rate in our question. So we can say that 0.500 is equal to K, which becomes our X value, what we're solving for, times 0.500 times, oh, sorry, not 0.5, 0.050 times 0.1. Okay, so what's our value of K? I like 100. What's our units? So our overall, we said that S, right, is going to be, S will be -1. We said this was negative. What's our overall rate order? 2 minus 1. So that will be molarity to the -1. So K will be 100, 1 over molarity times seconds. So it's like that. Sorry. Okay, and if we looked at this step here, right here we have 0.5 molarity over seconds divided by 0.005 molarity squared, because we multiplied 0.05 and 0.1 that both have a molarity concentration. So that squares that unit. Does everyone see how we got to the units of K? Anytime you have a second order overall reaction, those will be your units. Not to give you something else to memorize, but if that is something that you recognize, then you can kind of give yourself a check there. So if it was third order, then it would be 1 over m squared times s, right? Because we have s -1 times molarity to the -3 minus 1, right? Okay, and then what about question 4? Okay, so now we have if the concentration of A is 0.1 and the concentration of B is 0.4, what is the rate? We can assume K is the same as above. So what are we doing now? Yep, we're solving for the rate. So we can say that rate is still equal to K 0.05, or sorry, K A times B. We know that we don't know our rate, but we know that K is 100 molarity. Oops. 1 over molarity times seconds. We know A is now 0.1. And we know B is 0.4. So what is our rate? Our rate is 4. What's our units? Molarity over second. How does that differ from the 0.5 that we have? Does anyone know? Just kind of say it again. Yep, it's more concentrated. So one thing you'll notice about first order reactions is that whenever you double your concentration, your rate will also double. Okay, so when we looked at A was 0.1 in our second equation and 0.5 in our first equation. So based off of that, we would expect the rate to double one time just because of A, right? It doubled one time, so our rate should double. So if only A was changing, then our rate would be then 1, right? Because we went from 0.5 to 1, so we're going to go, or from 0.05 to 0.1, so we went from 0.5 to 1. How much did B change from 3 to 4? Or from question 3 to question 4. We were at 0.1 and now we're at 0.4. It went up by 4, right? So if our concentration is going up by 4, how much do we expect our rate to go up by? Also by 4. So we had our concentration doubling because of A and quadrupling because of B. So overall, it went up by 2 times 4, which is 8. And if you right? 0.5 to 4 is 8 times faster. Okay, that's how you're going to do a lot of your empirical data or your experimental data when you're trying to solve for your weight laws and try the overall order for your reaction. Okay. Does that help with your rate laws and practice problems with them? Yes. Okay, anything else you want to see today, or you feel a little bit better? Feel good? Okay. Is there anything you would like to see from me before your next exam? This is the homework again? Did that help with my solutions and everything? Yes? Okay. Awesome. And I'll be here again next Wednesday, and we'll stay probably for 2 hours again to kind of go over some stuff. In the meantime, if you have any questions, let me know. Feel free to email me. I tend to get back to you if I'm not super busy and swamped with my own stuff. And I think I Zoom recorded this. We'll see. So if that's the case, then I'll post this so that you can go back and watch it. And hopefully if you're not here 1 week, then you can do it that way as well. Was this okay with this on the board? Yeah, awesome. Okay, cool. Thank you.